Alright, today what we're going to talk about is titrations. Okay, and we're going to do a little bit of math and we're going to do a little bit of explanation of what titrations are. Okay, first off, we got to do some definitions on this stuff. Now, with definitions, first thing is what a titration is, okay? And a titration is simply something where we use to find the concentration of a solution using a solution of known concentration. Okay, now I know that kind of sounds like gibberish, but if we define a few other terms first, and then we'll do some math, and then we'll get some practical experience in class. So first off is what's called the analyte. Analyte is the solution with the unknown concentration, and a titrant is what is known as a solution with the known concentration. It's what's called a standard solution. Okay, a standard solution. Now, with that being said, for this one, the next thing that we need to do is define a couple of other points or places that happen with a titration. First off, we have the equivalence point. The equivalence point is when equal numbers of moles of acids and moles when equal numbers of moles of acid and moles of base are present. So essentially what you get is the fact that you're right at equal amounts. So there is no limiting reactant, there's no excess reactant. You have figured out exactly when the moles are completely equal to each other. Okay, and that's what the equivalent point is going to be. Now, an endpoint is when the color of an indicator changes. And we saw some of these indicators with pH paper and with the red cabbage juice. Okay, so we saw some of this when we talked about indicators. And if not, hopefully we'll get a chance to see some of these at some point. Now, the equivalence point, like we said, is usually marked by the color change. So what you're trying to do is with acid-base reactions, you're not going to get bubbles. You're not going to get heat. Well, you may get some heat rather, but you may not get flame, so you may not get energy produced as heat or as light. You may not put energy there. You're not going to get a precipitate. So what we have to do is we can get a color change, but in order to get a color change, we have to put in an indicator that's going to tell us when the reaction is done. So that's part of why we have to add these indicators and why they're important. And like we said, acid-base indicators are used to mark the equivalence point or the end of a titration when you have completely reacted everything with something else. And it only works if you choose a indicator whose endpoint is the same. Now, we're not going to get into choosing them this year. That's not part of what we're going to do. They're typically complex molecules that are weak acids, but in essence they change colors when the hydrogen ion is removed or reacted from something else, because with most of the time with acid bases we're dealing with the hydrogen ion reacting with hydroxide if we're talking about Arrhenius. Okay, now so for indicators, this one down here just shows you an example of what's called bromethymol blue indicator. Okay, so what happens over here, you have your acidic solution and it's yellow. Okay, you've got extra hydrogen ion floating around and the hydrogen ion has this nice yellow color. Now what happens is as you add more hydroxide, some of it reacts with the acid to neutralize the hydrogen ion to make water, and then you get to your equivalence point, and as soon as you add in extra hydroxide, it turns blue. So in essence what's happened is here it's still reacting, there's enough of both, enough of both, enough of both. Here you go past or right at the equivalence point, and as soon as you have one ion of extra hydroxide, it's going to start to turn blue. So it lets us know that the reaction is over, and hopefully we'll get a chance to even do a simple titration to give us an example. Now this slide is nothing for you to memorize, so do not try to memorize this. It's just to show you that there is a big range of indicators and that you can pretty much, if you know your equivalence point, which is a higher scale that we're not going to get to this year, you can find an indicator that will work for you. Okay, so that's indicators. They change colors with acids and bases based on pH. Now, some other indicators that are out there, besides those that are listed, there's universal indicators, and we did the red cabbage juice as a universal indicator. It had a little bit of a bigger range, but a universal indicator will just change different colors dependent on the pH. pH paper is essentially the same thing. It's paper soaked in the universal indicator, and we use those charts in order to match the pH. Okay, so that goes pretty simply. And then lastly, we also used a pH meter to determine pH, and this measures the voltage between electrodes, because remember pH is determinant on how much hydrogen ion or hydronium ion is present. Oops, H3O. Okay, so if those are charged particles, there's voltage, and plus it gives us this nice digital readout, which is easier. All right, the last thing that we need to do is some math, and there's two types of math problems that we're going to do with molarity and titrations this year. The first is using molarity as a conversion factor. Okay, if we remember, molarity is capital M, which we can write it out as moles per liter. So now what we have is another way to go in and out of moles. All right, with all of our units we've done throughout the year, we should remember that we can go from moles to grams using molar mass. We can go from moles to numbers of atoms or molecules using Avogadro's number. We went from moles to liters of a gas using either PV equals nRT or 22.4 liters per 1 mole if it was at STP. Okay, now the last piece is being able to go from moles to liters of solution using molarity. Okay, and that's what I'm going to take you through right here. So this little chart, you've seen this in the room. It's a concept map that's hanging up near the front, but all the different ways we can get in and out of moles, which ultimately allow us to do stoichiometry. We're going to keep it simple here though. Okay, so for number one, how many moles are there in 50 mils of a 0.4 molar hydrochloric? And number two, we're going to do the opposite. So number one, we're going to go from liters to moles. And number two, we're going to go from moles to liters. And I'm going to show you how to do that here on the next slide. Okay, so for example, for number one, the first one that we've got, what they've told me, so you may need to jot this down out to the side somewhere, is that we want to know the moles of solution. We're starting with 50 milliliters. Now we know molarity is liters, so I got to go ahead and in 1 liter, 1,000 milliliters. So it's going to be 0.050 liters. Now this is how we can use molarity as a conversion factor. Okay, we had 50 mils and we also have a molarity of 0.400, which is capital M, which if you remember is moles per liter. Now we want to go 2 moles, so we're going to put the mole unit on top. So we're going to have 0.400 moles per 1 liter. The math, it's on the top, so we're going to multiply both of these numbers. We had 3 sig figs in all of our data to start with, so if we take 0.050 times 0.4, it's going to be 0.02. We need 3 sig figs, so there'd be 0.0200 moles of, let me go back here for just a second, of hydrochloric acid for this one, okay? So again, it's just using molarity as a conversion factor. Now if you don't like this, you can still use the molarity equation. You just would have plugged in your molarity here, which would have been 0.400, your volume, which would have been right here, and again you're still multiplying those numbers. So it doesn't matter, but we need to start thinking of molarity as a conversion factor. Now the opposite way is this time we wanted to know the volume. So this time we wanted to know the liters. We were coming from moles. They told me that I had 3.00 moles and that I had a molarity of also 3.00 molarity, which remember is moles per liter. Now the math is going to be pretty simple on this one, but still just to show you the setup, we want to go from moles to liters. So I start with 3.00 moles, and this time I want to go 2 liters, so I need to put the 1 liter on the top. Okay, so remember we can think of molarity, the unit, if it's a molarity unit as moles per 1 liter, and I put the 3.00 moles on the bottom. 3 divided by 3 is going to be 1, so in 1 liter of a 3 molar solution I have 1.00 I'm sorry, if I wanted 3 moles in a 3 molar solution, I would need exactly 1.00 liters in order to obtain that. Remember, you also could simply plug and chug. Capital M is moles per liter. You're solving for the liters, so this essentially just sets up the math for you. If it was 3.00, you need to divide anyway to get that answer. So it's just another way to do it. Okay, the other type of math problems that we're going to do with titrations are all going to involve M1V1 equals M2V2. Now I'm simplifying it a little bit here, and if you continue your chemistry career you'll see that, but for right now, if we're doing a titration, we're going to pick a 1-to-1 molar ratio. So instead of going from liters to moles, and then either using your stoichiometry chart to go moles change in X from one substance to something else, and then having to go back to liters, M1V1 equals M2V2 is essentially a shortcut. And so that's how we're going to do this to make life easier. So if we read this, we're going to titrate a 25 ml solution of hydrochloric acid. So this is our volume, our first volume, V1, using a standard solution or a stock solution of 0.5 molar sodium hydroxide. So this is going to be my M2, since I already assigned the volume to the hydrochloric acid. Now we had to add 13 mils of sodium hydroxide, so that's my V2. And we want to know the original concentration of the hydrochloric acid. Okay, so if we do our little known and unknown here, we're looking for the molarity of the hydrochloric acid. And remember, my volume to start with was 25.0 mils. I also know that my molarity of sodium hydroxide is 0.500, and that my volume added is 13 mils. Now, one thing to note, so long as the volume units are the same, it doesn't matter. It does not have to be in liters here, unlike molarity that has to be in liters. Okay, so let's set this up here. Well, I've got M1 V1 equals M2 V2, and hopefully we'll get to see a sample of this in class, but the equipment that we usually use, and I want you to write this down because I'm going to ask you about it. This is a burette, okay, and this has up to 50 milliliters of stuff in it. Okay, so this would have our sodium hydroxide that to start with we know is 0.500 molar. What you do is you put your hydrochloric acid down here, and here you have your 25 mils of hydrochloric acid. What we're looking for is the concentration, the molarity of this solution. We know the molarity up here, and we know the volume. Now here's the deal. If you start with 50 mils, it told me that it took 13 milliliters. So what would happen is you open up the burette and you added 13 milliliters. So it would drop down to 37 mils. So the difference between them would be 13 milliliters that we added in, and if we added in an indicator, we'd probably use phenolphthalein, it would turn pink. So as soon as we added the 13 mils, it turned pink, and it means that our titration was done. Okay, and we're going to do this titration just not with the burette. So there's my titration. So now here is my V1, if you remember, is where my 13 mils goes with the 5.5 molar, and the 25 mils, so we're solving for M1. So the math is exactly like we did earlier, except instead of doing a dilution, we're now doing a titration to figure out an unknown concentration. So I'm looking for my molarity of my 25 mils of hydrochloric acid. Remember, it doesn't matter which one you put if it's number 1 or number 2, so long as you have the right pairs together. We've got 0.5 and we've got 25.0. Nope, I'm lying here. That one should be not 25. This one is going to be 13. And again, they gave me all of this for this problem. I multiply these two numbers, divide it by 25, and I'm going to get 3 sig figs. So I'm going to get 0.260, capital M for molarity, of hydrochloric acid. Okay, so we're going to add molarity as a conversion factor, and we're going to do some titration math with M1V1 equals M2V2, and we'll do practice on this in class.